All right, shall we get started or are we waiting for a few minutes here?
It is time, so you can go ahead and get started. We have 21 great. People on the call.
Super, thank you. Well, welcome everyone. My name is John Parks. I'm a senior associate and by training a marine scientist with background in ecology and human behavior. I'm here today to talk about 5 ecological principles for in situ resource utilization and terraforming on Mars. This is something that was actually inspired by members of society members from the 22nd conference based off a paper that I presented at that time. It's a pleasure to be with you all today. So today's presentation will be divided into 4 sections. I'm going to begin with a brief introduction, go through the 5 principles, and then run through some brief discussion and a conclusion. And I'm hoping to have some time left over for discussion with the group. So I'm going to begin with a brief introduction. As we're all aware, here on Earth, humanity has had very significant influence on the natural world, particularly within the last few hundred years. And one of the things that we've learned and are starting to build a base of evidence through scientific inquiry is that the human well-being of people on Earth is deeply linked with the planetary health. So it's something that you see in newspapers and in mass media every day. There's growing awareness around the world that the linkage between human health and planetary health is very important. So this is a critical lesson as we leave Earth, leave our cradle and head to the solar system and beyond, to remember that our well-being is deeply tied to planetary health. Recognizing this, the United Nations several years ago, they developed what they call Sustainable Development Goals. There are 17 of these. I'm not going to go through them. You can learn about them if you're not familiar. There's deep literature now developed around these 17 goals. The idea is to use these goals to help drive and administer development here on Earth in a sustainable way so that planetary health that's linked to human well-being can be strengthened. This is an important objective that most of the world's governments have signed off on. The idea is to use these principles to guide development here on Earth in a strategic but also sustainable manner, or smart, quote unquote. Again, the idea is to link human well-being explicitly with the sustainability and environmental health of Earth. I was fortunate enough to be invited to be a part of a National Center for Ecological Synthesis. This is a U.S. center that's based out of the University of California, Santa Barbara. And this, I was invited to be a part of a working group that looked at how to measure each of these 17 sustainable development goals. And you can see here in this photo, I'm there on the bottom center. Measure whether or not development objectives are being met in the context of human health and planetary health. So this gave us some important insights, and some of which I begin to start thinking a little bit about interplanetary health and human well-being. So really, a few years ago, I started thinking about, during the National Science Foundation initiative at the NC Center, started thinking about whether or not we could build a practical framework to guide the settlement and transformation of other planetary bodies, including Mars to begin with. And so in this sense, it's linking human well-being with interplanetary health, building upon the lessons that we've learned here on Earth. A few years ago at the 22nd annual convention, the Mars meeting, I was fortunate enough to be able to provide some findings from that initial framework that I developed. There are a few pieces here related to that framework, some assumptions that I had. 3 phases of initial human settlement on Mars: initial colonization during the first 25, 30 years, followed by permanent settlement, and then persistence after about 10 generations or 250 years of human beings on Mars. There were a number of environmental factors to consider here. Biological diversity is not applicable at the moment, but after terraforming, there may be some diversity that's introduced and needs to be considered. Complexity of ecosystems is as we understand it currently, is low or not applicable. but again, could be introduced and become important for consideration. The habitability is one of the most hostile places for humanity at the moment. That will change through time. And then a high level of dependency initially on Earth resources, focused resources being brought to Mars for settlement, with a change from in situ resource utilization through time that become less dependent on Earth. So, as I presented a few years ago, I outlined 13 relevant sort of values-driven factors that relate to the development of Mars. Again, these were inspired by what we've learned here on Earth. I presented these at the 22nd conference. I'm not going to repeat that. If you're interested, you can learn more from the recording from that presentation at USC. But essentially, in summary, this framework evolves through time, from early settlement through permanent settlement. It has a focus on linking the human well-being with interplanetary health. The idea was to guide some initial thinking around development on Mars. And in particular, I heard from a number of people both during the immediately following the presentation, and then in the weeks after I gave the presentation, a number of Mars Society members reached out and they asked me, independently, they were inquiring around factor 10, which is this bioengineered ecological succession, as an important factor to develop Mars. A few of the members independently asked me, what I was thinking in terms of how to guide or principles upon which to begin thinking about how to do this sustainable terraforming and in situ resource utilization. And so that got me thinking, and that brought me over the last 18 months to these 5 ecological principles that, again, as inspired by the society members themselves. Thank you all. I've done a little thought and happy to present today. So this is both in the context of in situ resource utilization, but then also the broader implications as Mars begins to be terraformed, and the ecological considerations as that ecology begins to be built out. So principle 1 is that I recommend that moving forward, it's going to make the most sense to take an ecological or ecosystem approach to both in situ resource utilization and eventual terraforming. Now, because there's not a deep ecology on Mars at the moment, this may not make sense at this time, but in a few hundred years, it's going to be very, very important. We can define it, taking an ecosystem approach as looking at management of the entire system of all the organisms and non-living resources within that system, including human beings, rather than looking at a specific resource like water ice, or looking at a specific organism that may be introduced. So 2 recommendations here. For in situ resource utilization, if you take an ecosystem approach, that's going to change how that is done. So rather than looking at extractive planning for in situ resources by resource, you're going to need to be thinking about the assemblage of the existing resources, how they may or may not interact now, as opposed to a few hundred years when terraforming is already underway. So the existing non-living and perhaps the microbial, if there's some living resource, but especially around the non-living resources, it's going to be very important to think about the ecosystem approach in the context of where we're going to be going. And I'll talk a little more about this in the presentation. Also, a second recommendation in taking an ecosystem approach will be to, as genetically modified organisms for the Martian environment are beginning to be introduced deliberately to build that functional structure for life outside of the dome, so to speak. We are going to need to be thinking about not introducing them species one at a time, or organisms that, or deliberate introductions one after the other, but rather as an assemblage. So actually planning and creating that assemblage of genetically modified organisms and keeping them together in their community structure, introducing them as a unit, rather as an assemblage, rather than individually that are phased through times. This is really important because of the ecology, the functional structure that will be intended is going to require that those organisms interact from the start, that the assemblage is essentially introduced as a whole rather than pieces being brought together through a phased approach. A second principle that builds off of this ecological approach is to embrace and actually facilitate ecological succession within the context of Mars, which essentially right now is nearly a dead body, is to the best of our knowledge. You can think of ecological succession as this process that changes the structure of the ecosystem over time. So all ecosystems undergo, they're stochastic, they go through change, sometimes chaotic. They're very difficult, they're complex systems, they're very difficult to predict. And so as we begin to terraform and modify the Martian environment for eventual suitability with genetically modified organisms, we need to really think about succession. So there are two recommendations, actually three here, that I'd like to make. First is if we think about what are known as R selection species. These are initial organisms that are, they're relatively low in biomass. They're highly fecund. They reproduce very quickly and have a lot of offspring. They're very dispersed. They're sort of opportunists. They can occupy many different niches. They're very important in the outset of succession in terms of pioneering and getting a foothold. And they're often, you can think of them as the foot soldiers. So that these are selection species, making sure that the genetic modification includes a fair proportion of the R species can be very important. It may make sense to think proportionally and test out what proportion of pioneer species, R species, versus others makes for that optimal mix in the Martian environment, which is completely different. But even at a genetically modified level, it's going to be completely different than Earth. We may see some interactions with pioneer species that we don't predict because it is on a different planetary body. But we need to think very carefully about how to introduce and making sure to introduce early these high productivity, essentially low cost, high value species and to help them get a foothold. Now, again, borrowing off of the previous principle, we need to be building a community of these, not introducing them one at a time. So later, with larger biomass, higher value, longer living, and far less fecund, so lower reproductive energy, we need to start introducing larger species that are case selected. So these are the organisms that are going to help bring more equilibrium and balance. They will depend on the R selection species, the early pioneers, what will help to build that larger structure. Again, we're going to need to think about the timing for introducing these genetically modified organisms, their specific trophic role. Are they predators or herbivores, or how to build those modified organisms in the ecology of Mars in order to build that equilibrium and to stabilize the terraformed structure. Now, in situ resource utilization will be going on around and within these areas, and it's very important to think about the interactions between the areas that are being terraformed and the areas that are being extracted for resource use. There are interactions that to date, we may not be aware of, and that we'll need to be very conscious of in terms of the equilibrium that needs to be struck. And then finally, we need to be very mindful. These systems are likely going to be highly unpredictable. There may be cascading effects that unintended consequences of introduction of certain genetically modified organisms. And through time, as we build out facilitate that succession to build the ecology of the community of organisms that we're looking for the next 300 years, we'll need to think a little bit about how the in situ resource utilization, extracting out certain in situ resources will impact that system over the coming future. So succession is going to be a key principle to follow. A third principle is to embrace or really to accept disturbance in this system. Things like dust storms is pictured here from this NASA photo. Disturbance is a natural process. It is going to occur. We need to recognize its role. Disturbance regimes can be defined as these temporary changes in whatever conditions you're operating in. And that because of those changes, there's a alteration, or in some cases even a shift in which organisms are dominant and how they're using or extracting from the existing resources. So recognizing the disturbance regimes are going to occur, and we have ample evidence that they do occur regularly on Mars. We need to think about this in terms of not only in situ resource utilization, but also in terms of terraforming. A couple of recommendations I would make, that I would offer. First, when we were able to predict intermediate disturbance events, not seeing them as natural hazards rather, but recognizing that there's a role for them, we want to manage them. We want to do our best to sort of manage that process so that these systems that are being both extracted from and built into, that there's some disturbance introduced into those systems, that the disturbance impact can be measured. We do know that on Earth, at least, that the genetic fitness and by exposing systems to disturbance, sometimes that's the only way they can produce. Fire regimes and forests are a good example of this, where certain conifers only release, they're only able to germinate following a fire. So it could be that in the future that species diversity on Mars may in part be dependent on travel through or release following a disturbance event like a dust storm. So we need to be mindful of this, think a little bit about species diversity that we're trying to build out, a community composition we're looking for, and then to try to optimize those disturbance events so that they can build in some of that genetic fitness. Now, there will be, of course, acute events that are very significant and damaging, and the best that we can do is probably try to mitigate that, recognizing that if it's a very significant event, we may want to put in some mitigation mechanisms for those systems that we're trying to create and terraform to not only ensure that they have some adaptive capacity and able to withstand that and survive, but also so that we can better understand how the perturbation, the disturbance that's occurred in the system, how quickly those systems rebound back from a very acute event. So some really important things to think about in terms of not just in situ resource utilization and what happens after we extract certain things, but also looking at, as we put into the system, how disturbance systems regimes on Mars affect those systems. A fourth key principle is habitat fragmentation. This can be defined as the splitting apart or division, and then therefore increasing isolation of patches of habitat. In this case, this would be terraformed, deliberately terraformed habitat. You can also think of in situ resource utilization as essentially cutting a path through existing habitat. And so where you're extracting from the existing surface, you're going to alter that, and you're basically breaking up what was there originally. And we know that in Earth analogs, that where you have more fragmented habitat that basically differs from what was originally there, we have lower integrity. And especially as we begin to build out the terraformed systems, that lower integrity leads to things like lower genetic fitness and genetic drift, and then overall the ecosystem is degraded. So there are a couple of recommendations here that we want to think about. First is to balance the spatial proportion. So where we're using extractive repurposing techniques for pulling out using in situ resource reutilization techniques, pulling out certain inorganics or minerals, versus the areas that we're terraforming, we're actually introducing and putting in bioengineered material. And so thinking about balancing the proportion and distribution of this will help to minimize the effects on the terraformed habitat. And then also, as we move forward in the next 100, 150, 130, 40, 50 years, over the next 100 plus years, we are going to need to think a little bit about how, once those areas are terraformed, we want to avoid building out terraformed patches. We want to think a little bit about, into the future, a little bit about where a large area of terraformed habitat will occur. We do know, if you look at artist conceptions, you'll sometimes see that against the Martian landscape, they'll have little patches of habitat, of green space that has been terraformed and genetically modified to persist outside the dome. We need to avoid that. We need to think about large areas that are either contiguous, they're concentric circles of habitat that are able to persist with one another at a core center, probably human settlement at the center, or a large contiguous area of that community of habitat, in order to avoid the patchiness and the edge effects that occur where you have fragments and you have along the perimeter, you have these perturbations that really limit the ability of those populations to persist through time and to success through time. A fifth and final principle I'd like to raise here, which is sort of the largest scale, so I'm putting it number 5, is taking what we know about landscape ecology theory and applying it to Mars. Now, it's going to look really different on each interplanetary body because of the natural conditions that occur there. that will be subsequently amended by terraformation. But you can think of landscape ecology theory as this study about how human impacts, in particular, how they impact or how they have an effect on the landscape structure and function. And this is not only looking at disturbance and sort of extraction, but then also on recovery and mitigation, and how to seek stability with the human interaction in that landscape. In a Martian environment, the landscape I would recommend should likely include not just the surface, but also underground, the subsurface, which is probably where a lot of the terraforming will start. And then also under dome. You can think of the underdome as the analog here would be in a cityscape and sort of building urban gardens and things like that. So a fairly different model than what you would see out on the surface, perhaps away from the domes. But nevertheless, we need to think about it, landscape ecology in the context of both underground or subterranean, and then above and in the dome. I would recommend that we begin now, soon, to start thinking about how to design what the optimal network, and there are algorithms that you can use. There's models that you can run through a statistical regression to look at maximizing and minimizing costs and maximizing benefits for this. But designing a network where you have a multiple use of in situ resource utilization, which is extraction essentially, coupled with where you're going to be introducing in bioengineering, terraforming, and then interweave areas where there are reserves, where there's no activity, there's no extraction or no use of in situ resources, nor is there modification through alteration. Thinking a little bit about that configuration, the current administration just recently announced an initiative to try to set aside a reserve. I think it's 30% of the oceans. So you know that some of this political and practical thinking is already occurring here. I would recommend that we get a start on this rather than being reactive, that we be proactive on Mars and other interplanetary bodies that we are going to inevitably occupy. So that's a quick overview on the 5 principles. I have a couple slides on discussion before I close. If these 5 principles are applied, there's some really practical utility. First, you're going to greatly expedite the transformation of in this case, Mars. Second, you will, as I mentioned earlier, you'll be able to maximize on ecological processes like succession and maximize integrity of those systems as they're built out. And then you'll also minimize the negative effects of over-extraction, perhaps accidental or deliberate, of in situ resource utilization, and the associated scarcity that might come from over-extraction. So there's a really practical application for using these ecological principles. There's also a secondary utility. First, it is consistent with the UN's vision about Earth. It allows us to bring some sustainability principles into our first foray into an interplanetary, an off-world, and making sure that we're bringing those principles and thinking about ecology in the system and the role that humans will play in that as we expand out. It'll also allow us to demonstrate early adaptation into how we do interplanetary development. And then finally, and very importantly, it may help to mitigate or minimize competition for existing resources that can be found in Mars or near asteroids or in the asteroid belt or in other ocean worlds like Enceladus. There are going to be resources that are found there. They're going to be important economically, and so minimizing competition and conflict over those resources is going to be very important. So applying some of these ecological principles that we've had very hard lessons in here makes good sense. So just in conclusion, I do believe that the lessons that we have learned here about how human health is deeply linked with the health of the planet. We should recognize that and be ready to adapt that for interplanetary use, no matter where we go. And then just as importantly, by doing this, we're demonstrating our values. We're applying the values that we're bringing as a species as we move forward beyond the cradle into the solar system and beyond, that we're really bringing those values forward and the learning that we've had from Earth and representing that as we move into colonizing other worlds. So I'd just like to thank, again, my thanks to those of you that reached out, the members and the attendees at this 22nd Congress, that the convention that reached out. My thanks for you for inspiring this. And my thanks to my colleagues at the National Center for Ecological Analysis and Synthesis and the funding from U.S. National Science Foundation. Thank you.
Oh, thanks. Yeah, so we have about 5 minutes left, and I have some questions from the audience for you. So the first here is, what do you think of McNamons's thesis of applying fungi in the Martian environment to initiate life on land?
I think not only fungi, but that there are a number of invertebrates that are going to be very important to introduce. I think that it's, I'm of the belief that a single species approach, while compelling and probably less costly and more practical, sounds good. I do think that thinking about introducing a system of supporting organisms and understanding how they would interact in the environment may be a better approach, particularly if there are disturbance events where those organisms alone would have a hard time persisting following the event, versus if they're able to work together as a community and able to function as a system and therefore have greater fitness against that perturbation. Of course, I think we're going to have little choice but to test out many specific species in sort of controlled settings, whether they be on the surface in a controlled environment or in a lab. We do that now, and it's very revealing to do that experimental approach. But eventually, I do think we'll move to essentially ecological restoration, even though we're not restoring. It's essentially primary succession. We're taking essentially a dead body and we're introducing communities of organisms rather than individual species. Thanks for the question. Great question.
Yeah, so next question is, what does Mars gravity do to affect your organism choice? For example, maturity size?
Yeah, no, and this is a very important question, not just for biomass and sort of the size of reproduction, but then also grow out and the requirements for reaching a certain biomass that would allow for reproductive age. I do think that, smaller and lower biomass organisms, as I mentioned earlier, are going to be important to introduce as a community. Those R species, those pioneer species that are high value but low cost, highly fecund, short-lived, are subject to perturbation and have high mortality if disturbed, but are easily able to reproduce rapidly. Those tend to be smaller biomass and maybe easier given the current conditions to introduce. And then through time, as humans begin to change the atmospheric conditions and barometric pressure and not just the sort of atmospheric conditions, but even the soil, the regolith, as it begins to change, I think it will be important to start to look at how to genetically modify organisms to persist in lower gravity and with those environmental conditions to ensure that they have a higher likelihood of success. With time, we may find that some organisms with minor modification may actually do well. This may be 300-400 years in the future, but I would suspect that based off of our experience here, that we will likely find ways to essentially import near hybrids or near similar organisms from Earth, and at least some of those K species or high biomass, they may persist in once the environmental changes have been made. Thanks for the question.
Yeah, and we have about 1 minute left. So what is the minimum air pressure required to introduce the first organism?
Yeah, I would say that, the air pressure now is probably sufficient to introduce, as thin as it is and as hostile as it would be to large mammals like ourselves. I do think that there are certain organisms that could be introduced now. I know that a number of people have talked about everything from the fungi to microbes. Algae is another one that I think will get increasing attention, particularly if it can be modified. And I think, again, as part of those opportunists, those R species, R selection species, identifying those that can persist under current atmospheric conditions is going to be very important. Thanks for the question.
Yeah, and it's time now for the next workshop sessions. But
Thank you all. Appreciate your time.
yeah, thank you.